Hey guys! Welcome back to the laboratory. In this video, we are looking at the limiting reactant. By the end of this video, you should be able to define the term limiting reactant and use calculations to determine the limiting reactant in a chemical reaction. So, let's go! In any chemical reaction, the reactants will react with one another and are used up to form the products of the reaction. For example, in this reaction, reactant A must react with reactant B to form our product. If reactant A is used up during the reaction before reactant B, then the reaction will stop, as there is no more of reactant A for reactant B to react with. In this scenario, we call reactant A the limiting reactant, as it's the reactant that is used up first, and therefore limits the amount of product that can be formed. In turn, product B is referred to as the reactant that is in excess, as it is not used up first during the reaction. We can use calculations to identify the limiting reactant in a chemical reaction, and in turn, calculate the maximum amount of product that can be formed. For example, 2.7 grams of aluminium reacts with 9.125 grams of hydrochloric acid to form aluminium chloride and hydrogen. State the limiting reactant in this reaction, and calculate the mass of aluminium chloride formed. Before we begin any calculation, it is crucial that we first check the equation and ensure that it's properly balanced. There are an equal number of atoms of each element in the reactant and products of this reaction, meaning we can continue to the first step of our calculation. The first step of this calculation requires for us to convert the mass of each reactant into moles. We can achieve this by using the following equation, where moles is equal to mass divided by relative atomic mass, or relative formula mass. To calculate the number of moles of aluminium, we must do 2.7, which is the mass provided to us in the question, divided by 27, which is the relative atomic mass of aluminium, giving us a total of 0.1 mole. To calculate the number of moles of hydrochloric acid, we must do 9.125 divided by 1 multiplied by 1 plus 1 multiplied by 35.5, which is the relative atomic mass of hydrochloric acid. This gives us a total of 0.25 mole. Next, we must use this information to determine the limiting reactant. The balanced equation tells us that 2 mole of aluminium reacts with 6 mole of hydrochloric acid. We can simplify this ratio to 1 mole of aluminium reacting with 3 mole of hydrochloric acid. This ratio indicates that for every 0.1 mole of aluminium, we need 0.1 times 3 mole of hydrochloric acid, which is equal to 0.3 mole. In step 1, we calculated that we only have 0.25 mole of hydrochloric acid. Therefore, hydrochloric acid is the limiting reactant. The final step of this calculation will now allow for us to identify the maximum mass of aluminium chloride that can be formed in this reaction. Once again, if we look at the ratio of molecules in the balanced equation, we can see that 6 mole of hydrochloric acid is needed to make 2 mole of aluminium chloride, which can be simplified to a ratio of 3:1. Remember that the limiting reactant will determine how much of your product you can make, so at this stage it's important for us to only focus on the ratio between the product we are trying to find the mass of and the limiting reactant. The ratio of hydrochloric acid to aluminium chloride tells us that for every 0.25 mole of hydrochloric acid we have, we will make 0.25 divided by 3 mole of aluminium chloride, which is equal to 0.0833. We can now rearrange this formula to calculate the mass of aluminium chloride formed, where the mass is equal to the number of moles multiplied by the relative formula mass. 0.0833 multiplied by 1 multiplied by 27 plus 3 multiplied by 35 is equal to 11.12 grams. The maximum mass of aluminium chloride that can be formed during this reaction is 11.12 grams. This concept is quite tricky to get your head around, so let's talk through another example together. In this example, 2.4 grams of magnesium reacts with 2.4 grams of oxygen to form magnesium oxide. State the limiting reactant in this reaction and calculate the mass of magnesium oxide formed. As mentioned in the previous example, it's crucial that we first check the equation and ensure that it's properly balanced. There are an equal number of atoms of each element in the reactants and products of this reaction, meaning we can now continue to the first step of our calculation. The first step requires for us to convert the mass of each reactant into moles. We can achieve this by using the equation moles is equal to mass divided by relative atomic mass or relative formula mass. To calculate the number of moles of magnesium, we must do 2.4 divided by 24, giving us a total of 0.1 mole. To calculate the number of moles of oxygen, we must do 2.4 divided by 2 multiplied by 16, giving us a total of 0.075 mole. Next, we must use this information to determine the limiting reactant. The balanced equation tells us that 2 mole of magnesium reacts with 1 mole of oxygen. On this occasion, this ratio cannot be simplified further, so we can leave it as it is. This ratio indicates that for every 0.075 mole of oxygen, we need 0.075 times 2 mole of magnesium, which is equal to 0.15 mole. In step 1, we calculated that we only have 0.1 mole of magnesium, therefore magnesium is the limiting reactant. The final step of this calculation will now allow for us to identify the maximum mass of magnesium oxide that can be formed in this reaction. Once again, if we look at the ratio of molecules in the balanced equation, we can see that 2 mole of magnesium is needed to make 2 mole of magnesium oxide, which can be simplified to a ratio of 1:1. The ratio of hydrochloric acid to aluminium chloride tells us that 0.1 mole of magnesium is needed to make 0.1 mole of magnesium oxide. We can now use this formula to calculate the mass of magnesium oxide formed. 0.1 mole multiplied by 24 plus 16 is equal to 4. The maximum mass of magnesium oxide that can be formed during this reaction is 4 grams. Here's an example for you to try. Pause the video and take your time to work through the question. Press play once you're ready to check your answers. As previously demonstrated, your method should have started with checking that the equation provided was balanced. Then, we would calculate the moles of each reactant given in the question. The number of moles of iron is equal to 0.089, and the number of moles of sulfur is equal to 0.156. Next, you were to find the limiting reactant. The balanced equation tells us that iron and sulfur react with one another in a 1:1 ratio. Therefore, 0.089 mole of iron is reacting with 0.156 mole of sulfur. There is less iron than there is sulfur, meaning that it will be used up first, and therefore iron is the limiting reactant in this reaction. Finally, we must calculate the maximum mass of iron sulfide that can be produced in this reaction. The balanced equation shows us that 1 mole of iron reacts with 1 mole of iron sulfide. Therefore, 0.089 mole of iron reacts with 0.089 mole of iron sulfide. We can now calculate the mass using the equation 0.089 multiplied by 56 plus 32, which is equal to 7.8. The maximum mass of iron sulfide that can be formed during this reaction is 7.8 grams. Anyway, that's it for this video, guys. Thank you for joining me in the laboratory. Please leave a like on this video if you found it useful, and don't forget to subscribe to the channel so that you don't miss another one. See you soon!